Good morning, friends. Today we are going to discuss series resonance in RLC series circuit. In RLC series circuit, when circuit current is in phase with applied voltage, the circuit is said to be in the condition of series resonance. Okay, so this condition is obtained in RLC series circuit. Under this situation, under series resonance situation, XL equals to XC. That means the inductive reactance is equals to capacitive reactance. Okay, so we can simply write that at resonance XL minus Xc equals to 0. So if we want to write the total impedance of the series RLC circuit, that impedance will be given by Z equals to R square plus XL minus Xc whole square. Applying series resonance condition, we can simply write Z resonance, this will be R square plus 0 square. Why? Because XL minus Xc equals to 0. So we will simply get the impedance of series RLC circuit under resonance condition ZR equals to R. So from this equation we can say that under series resonance condition the impedance of the circuit is only resistive. Okay, under this condition if you want to calculate current, that current will be given by IR equals to V divided by that impedance, or we can simply write V by R. Now we can see that the under series resonance condition that impedance is equals to R and the value of this impedance is very less. Why? Because XL minus XC is equals to 0. So the overall resistance, the resistance offered by the I would say the resistance offered to current will be very less. Okay, so in this condition we can simply say that since impedance is very less, so under series resonance condition the circuit draws maximum current. Okay, circuit draws maximum current. Okay, so this current will be the maximum current flowing in the circuit. Now second thing which is related with series resonance is resonating frequency. Okay, so resonating frequency is what? So as we know that the inductive reactance of the circuit XL is equals to omega L, which is equals to 2 pi FL, and X equals to 1 upon omega C, which can be written as 1 upon 2 pi FC. Okay, separately we can write it. So what we can do, we are changing the frequency of the supply, and as the frequency increases we can simply see we are changing the frequency. We are either increasing the frequency or this is nothing but the supply frequency. Okay, this is the supply frequency. So as we are increasing the frequency, since we can see that XL is directly proportional to F. Okay, so as we are increasing the frequency, definitely the value of XL will increase, and in this condition we can see that Xc is inversely proportional to frequency. So as we increase F, Xc will go down. Okay, so we can simply see that by increasing the frequency XL increases, whereas the value of Xc decreases accordingly. But at a certain condition, we see, or at a certain frequency we can see that XL equals to Xc. Xl equals to Xc, and that is the condition where resonance occurs, and under this condition the frequency is designated as resonating frequency. So I could write, I can write at series resonance XL equals to Xc, and if we put the value of XL and Xc here, 2 pi f L 2 pi f C, so directly we'll get, and since this is the frequency under resonating condition, so we can simply write Fr here, and if we solve it, we'll get Fr equals to 1 upon 2 pi under root of Lc. So this frequency here is the resonating frequency, or the frequency under series resonant condition, and its unit is hertz. Okay, where and the Ln and Lnc are the inductance and capacitance of the series resonating circuit. You can see I've already plotted a graph here. In this graph, as we are increasing the frequency, this is in x-axis we are having frequency, and y-axis we are having XL and Xc, which is inductive reactance and capacitive reactance. So as we increase the frequency, the XL increases accordingly, since XL is directly proportional to F, whereas as we increase the frequency, the Xc decreases. Okay, Xc decreases. So at this moment of time, this point here, for example, this is a point of intersection. This point, XL equals to Xc, I would say that at that particular point the resonance occurred. Now we can simply see that under this condition the current is maximum, because the impedance of the circuit is very low, the current is maximum. So under this condition, power under, I would say, PR, under this series resonance condition, this will be very high. Why? Because current is very high. Okay, so what I would say, in general I would say that series resonant condition general power system should be avoided. Why? Because it leads to more power loss. Okay, so in general, in power system at resonance, very high voltage developed across inductive and capacitors. Okay, so that may cause, definitely, if the very high voltage is developed across the contacts, it may damage the equipment. So therefore generally series resonance should be avoided in general power system. But in case of some of the electronic circuits, I would say TV receiver and tuning circuits, the principle of series resonance can be used, and it is used. Generally it is used. Okay, so series resonance as far as the power system is concerned should be avoided, but if the communication circuitry are involved, definitely we can use the advantage of series resonance, right? Now if we want to plot the graph between frequency and the current flowing in the series resonating circuit, I would make a graph like this. Okay, and at this particular condition here, this is IR. So this is what? This is IR, maximum value of the current. Okay, and this is the frequency where resonance is occurring. Okay, so this was all about series resonating circuit. Thank you very much.